So the first thing I'm going to do is use Hess's law of summation. I'm not going to spend time defining Hess's law of summation because I asked you to read the text about it. I'm going to give you a demonstration of how it works and point out where it applies here. But if you didn't read before you came, you're not in as good a shape now as you would have been. So I'm trying to encourage you to read. Right? So let's suppose we have this situation. There is a chemist, and she's seeking ways to convert carbon monoxide and nitrogen monoxide to less harmful gases. She works for Toyota. Okay? Toyota gotten a lot of bad press lately, so they want to do good things in my hypothetical example here. And a good thing would be to take the carbon monoxide and the nitrogen monoxide that occurs in the exhaust of any automobile that we have today, except the total electric ones, of course, and we're going to convert these chemically to carbon dioxide, which is less toxic than carbon monoxide, and dinitrogen, which is basically inert. So the question first is this a practical reaction to think about? And one aspect of that question, the answer to that question is, does this thing require a huge amount of energy? If it requires a huge amount of energy, maybe that's going to hurt the mileage of our Toyotas, right? And that wouldn't be a good thing because Honda's out there and they're going to claim that their mileage is better than ours anyhow. Okay? Maybe even General Motors. All right? So the first question would be, is this a practical reaction to be considering? And one aspect of that is it exothermic or endothermic? And if it's exothermic, that's good. All right? That gives us a little extra heat to work with. And then maybe we can find a way to make this reaction actually occur. So we're going to use Hess's law to do this. And Hess's law takes thermochemical equations and extracts information from them about other equations. That's what it does. And this equation, I put a T in front of it. That's my way of indicating this is the target equation. And what I would like to do is get delta H for this target equation. Work? All right. Here is the information we were able to look up about reactions of these species. First of all, carbon monoxide reacts with 1/2 mole of oxygen to make CO2, and this is a thermochemical equation. The delta H for this is negative 283 kilojoules. Notice it's not kilojoules per mole. It is kilojoules for this equation as it's written. It's per 1 mole of CO2, but it's 1/2 mole of oxygen and 1 mole of CO, so we just write it as 283 kilojoules. Delta H's of reaction are not kilojoules per mole. Then there's N2 plus O2 goes to 2NO. This is called the lightning reaction because in lightning bolts, nitrogen and oxygen from the air combine to make NO. And this thermochemical equation says it takes some energy, 180.6 kilojoules, to convert 1 mole of N2, 1 mole of O2 to 2 moles of NO. Now, Hess's law allows us to extract the information about delta HT from these two because, don't miss this, every part of the target equation is covered in these two equations. If anything was missing, we wouldn't be able to do it. But it's all there. CO is there, NO is there, CO2 is there, N2 is over here. Everything is there. So that means if we are careful, we should be able to get the answer to this. What Hess's law says is if you adjust these two equations, A and B, in such a way that they add up algebraically to the target equation. What I mean by that is we can turn them forwards, backwards, we can divide them all by something or multiply them all by something and do the same thing for their delta H's, of course. If they add up to the target equation, then the delta H's will add up and we'll have our answer. So now we have to think. And in thinking about this, and if you look at A here, A has carbon monoxide as a reactant, and it has carbon dioxide as a product. So I'm thinking we leave A alone. It already looks like it's in pretty good shape for what we want to do. But B, on the other hand, has NO as a product, and we need NO as a reactant. So we're going to have to turn B around to begin with. And then it has too much nitrogen monoxide. So we're going to have to turn B around and divide it by 2. All right? Now, so in altering these things, we're going to leave equation A alone, and we're going to turn B around, reverse B, and multiply it by 1/2 or divide by 2, hopefully the same thing. So here is the turned around equation B. 2NO goes to N2 plus O2. The delta H for that would be minus 180.6. And then we're multiplying that by 1/2, so the delta H would be minus 1/2 of 180.6. So the altered equation B is NO gas goes to 1/2 N2, multiplying everything by 1/2 here, plus 1/2 O2, and the delta H is negative 90.3 kilojoules. Is everybody comfortable with what we have done so far? You have a question? We turned it because we need the NO as a reactant, and we divided by 2 to get the amount of NO right. We need 1 mole of NO, not 2 moles of NO. Okay, so if you're comfortable with that, what I propose to do is to add this altered B equation to the A equation. All that's on the next slide. Here's the A equation. CO plus 1/2 O2 goes to CO2, and the delta H is the same as it was on the previous slide. Here is the altered B equation. NO goes to 1/2 N2 plus 1/2 O2. The delta H is what we calculated it to be, negative 90.3 kilojoules. Now, as you look at this, first thing I will point out to you is that 1/2 O2 on this side will cancel with 1/2 O2 over there, and O2 is now gone, and we don't have to worry about it. So now we'll algebraically add these two things together. CO plus NO goes to CO2 plus 1/2 N2, and that's the target equation. A miracle has happened, right? It really didn't take that much work. We just sort of lined them up, reactant and products, and got the amounts right, and then when we added it, all worked. So Hess, at this point, would say, oh, you did very good. You did very well. But now you have to go through this and add up the delta H's in the same way that you added up the reactions. And when you did this, the result would be negative 373.3 kilojoules to one too many significant figures. Okay? So the answer to the question is this looks like a good reaction. It's going to give off a significant amount of heat. And so all we need to do is to find a catalyst or some way to make these products occur instead of some other products. Questions? This is Hess's law of summation. And you use it whenever you're asked for the heat of reaction and you're given thermochemical equations. You see those two things? Red light goes on in your head. I've got to use Hess's law of summation. Oh, my God. Okay? It's not that scary. It really isn't. All right. I'm going to do another one for you. This one I made up. Or I stole it from another book. I'm not sure where I got it. The target equation is ammonia going to 1/2 of hydrazine plus 1/2 of H2, and they're all gases. I'm not sure whether you have this. It may be in a different place. You may not have it at all. But anyhow, write it down if you don't have it. So that's the target equation. And the two pieces of information that we have are thermochemical equation A, N2 plus 2H2 goes to N2H4. Delta H for that from tables is plus 95.4 kilojoules. Okay? And B is N2 plus 3H2 goes to 2NH3, and the delta H for that is negative 92.2 kilojoules. Okay. Now, in looking at this, we have to make some choices about what to do with A and B to make them add up to T. Okay? The first thing I would say is the only reactant is ammonia. The only place to get ammonia is B, and in order to get B as ammonia as a reactant from B, we have to turn it around, and then we also had to divide by 2 to get the amount right. So this is going to be minus B over 2. Sometimes I put these little things over here on the left side to remind me what I'm doing. I'm changing B around, and I'm dividing by 2. So if I change B around, it's going to be, to begin with, 2 ammonias goes to N2 plus 3H2. Pardon me. Delta H for that, we haven't divided by 2 yet, is equal to plus 92.2 kilojoules. Okay? And now if we divide by 2, we have to divide everything by 2. Ammonia goes to 1/2 N2 plus 3/2 H2, and the delta H for that is plus 92.2 over 2, which is 46.1 kilojoules. Okay, so this is minus B over 2. Now when you look at A has N2H4 as a product, which is a good thing. But it has a full one, and we need a half. So what I would suggest is we take A over 2. A over 2 over here. And so this would be 1/2 N2 plus 2H2 over 2 would be H2. And that would go to 1/2 N2H4. And the delta H would be plus 95.4 divided by 2 is plus 47.7 kilojoules. Okay. Now, if I did my preparation right, was there a question? If I did my preparation right, I should be able to draw a line under this. And now we're going to look at this one and this one. And I note right away that 1/2 N2 cancels here and here. Okay? And I have 3/2 H2 here and H2 here. Let's just add everything up and then I'll deal with that. NH3 plus H2 goes to 3/2 H2 plus 1/2 N2H4, and the delta H for that is the sum of these two is plus 93.8 kilojoules. But we've got hydrogen on both sides of the equation, right? So we've got to cancel out and get it on one side. So 3/2 over here, 2/2 over here, that'll cancel, and this will make 1/2 H2. So let's rewrite it down here. NH3 gas goes to 1/2 H2 gas plus 1/2 hydrazine and 2H4 gas. Okay, and look at that, a miracle's happened. Hess's equation has given us a miracle. We have the target equation. This is it. So delta H for this is equal to plus 93.8 kilojoules. This is an endothermic reaction. We're going from a more stable compound to a less stable compound, so that's uphill.